let's do a few more examples of calculus with parametric curves. So the first thing is to find the points on the curve where the tangent is horizontal or vertical. So to determine where the tangent line is horizontal or vertical, the first thing you need is the derivative. Remember that the derivative dy dx is given by dy dt over dx dt. So dy dt is 3t squared minus 6t, and dx dt is 3t cubed minus 3. Let's just simplify that slightly by dividing everybody by 3, and that's t squared minus 2t over t squared minus 1. And factoring, we find that this is t times t minus 2 over t plus 1 times t minus 1. So the tangent will be horizontal whenever this derivative is 0. So it's horizontal if t times t minus 2 is equal to 0, and that will happen when t is equal to 0 and 2. Now the thing to remember is that those are not the points on the curve, those are just the t values when the points occur. So you must figure out what the points are. At t equals 0, when you input that into the x equation, you have x is 0 cubed minus 3 times 0, or 0. And the y is also equal to 0. So at the origin, the tangent is horizontal. And at t equals 2, well, the x would equal 8 minus 6, or 2. And the y is 8 minus 3 times 4, so that's 8 minus 12, or negative 4. So at the point 2, negative 4, we have horizontal tangent, and 0, 0, we have horizontal tangent. Now the tangent will be vertical if t plus 1 times t minus 1 is equal to 0, which means either t is equal to plus or minus 1. And at t equals positive 1, we find that x is 1 minus 3, or negative 2, and the y is 1 minus 3, or negative 2. So at the point negative 2, we have a vertical tangent. And at t equals negative 1, we find that x is negative 1 plus 3, or positive 2, and the y is negative 1 minus 3, or negative 4. Sort of a strange thing happened there. You have a horizontal tangent line and a vertical tangent line at the same place. So here is another, that's actually okay. The problem is that these curves can double back on themselves, so you can actually have horizontal tangents and vertical tangents at the same place. The next example has that. So here we have a curve C that's defined by the parametric equations x equals t squared and y equals t cubed minus 3t. We are going to show that C actually has two tangent lines at the point 3, 0, and we're going to find their equations. So one way to find that there must be two tangent lines at this point is to observe that this 3 is the x value. So 3 is equal to t squared, which means this 3 arises when t is both positive and negative square root 3. So for each value of that parameter, you could get two different equations. You possibly could get equations of tangent lines that have different slopes, or even not different and different intercepts as well. So let's find those equations. So dy dx is dy dt over dx dt. So dy dt is 3t squared minus 3, and dx dt is 2t. And so at the point where t is equal to root 3, the slope will equal 3 times root 3 squared, which is 3, minus 3 over 2 root 3. So that's 9 minus 3, or 6 over 2 root 3, which is 3 over root 3, or simply square root 3. And at t equals negative root 3, the slope will be 3 times, still 3 because that negative root was squared, but the denominator is now negative 2 root 3, which will give us 6 over negative 2 root 3, which will simplify to negative root 3. So one tangent line has slope positive root 3, one has slope negative root 3, and the equations of those lines will be y minus 0 equals root 3 times x minus 3, or we can just say y is root 3 times x minus 3. That's one of them. And the other one is y equals negative root 3 times x minus 3. And if you graph these equations, 3, 0, go through 0, 0, it looks something like this-ish. And you can kind of see how that multiple tangent lines at one point could happen. So one of them has a negative slope, one has a positive slope, and so stuff like this can occur. If it occurs, you're not necessarily incorrect. Now the first derivative wasn't super hard, but the second derivative was a bit tricky. So this one we're going to find both the first derivative and the second derivative, and we're going to use the second derivative to determine when the function is concave up. So first, the first derivative, dy dx, well, that's dy dt over dx dt. So to find the derivative of y, you have to use both the product rule and the chain rule. So that'll be 1 e to the negative t plus t times negative e to the negative t. The reason that's negative is because the derivative of e to the negative t is e to the negative t times negative 1. And all that over e to the t. So you have e to the negative t minus t e to the negative t over e to the t. And you can, it'll be easier for us if we think about this as e to the negative t minus t e to the negative t multiplied by e to the negative t, and then distribute that e to the negative t, in which case the exponents add. So e to the negative 2t minus t e to the negative 2t. So there's my first derivative. If you'd like to, you could also write that as 1 minus t over e to the 2t. That's also okay. And actually that might be simpler, so we could use this form. So there's the first derivative. Now the second derivative, you find by replacing y by dy dx in that equation. So d dt over dy dx all over dx dt. So the derivative of this first derivative will be e to the 2t times negative 1 minus 1 minus t times 2 e to the 2t. 2 came from the chain rule, over e to the 2t squared, and then all that divided by dx dt, which is e to the t. So simplifying this slightly, let's factor out e to the 2t in the numerator. Then we'll have negative 1 minus 1, no, negative 1 minus 2 plus 2t over e to the 4t, and instead of dividing by e to the t, let's multiply by 1 over e to the t. Okay, so that gives us, in the numerator, 2t minus 3, And all those e to the things can actually do some canceling. So e to the 2t over e to the 4t, that's going to cancel out to e to the 2t. You could think about the previous step where you had e to the 2t squared and an e to the 2t in the numerator. You could have just canceled one there. So then multiplying, this would become e to the 2t. By this e to the t, those exponents add and you get e to the 3t. So there's the second derivative. We would like to figure out when this curve is concave up for which values of t. So we make a number line. We're going to talk about the sign of the second derivative. And we need to figure out when the derivative is 0. Well, it's 0 only at 3 over 2. And it's never undefined because e to the 3t is never 0. So for a number to the left of positive 3 halves, let's test 0. When you test 0, your numerator is negative, denominator positive, so your second derivative is negative on that interval. Past that point at, say, like, I don't know, 2, numerator positive, denominator positive, you're positive there. So the curve is concave up if you're on the interval from 3 halves to infinity. Probably should say, don't forget those are t values. Now, in addition to being able to find derivatives, we also are able to find antiderivatives and use these things to find areas and arc lengths and surface areas. So here we have a curve called an asteroid, and this curve is defined by the parametric equations a cosine cubed theta and a sine cubed theta, and it looks like this. Your book, this question came from your textbook, and the textbook had a picture of the curve. And you can convince yourself by plotting some points that this a value that corresponds to a value of theta equals 0, because when you plug 0 into this equation, you get a out and you get 0 out of this equation. This corresponds to theta equal to pi halves, so you're tracing it in this direction, much the same as the unit circle gets traced. So we're going to set up and simplify, but not solve, an integral that represents the area of this asteroid. So first of all, notice that you have a whole lot of symmetry going on here. So the area could be 4 times the integral from 0 to a of y dx. Now note that 0 corresponds to, like x being 0 corresponds to being right there, which means it corresponds to a bound of pi halves, and a corresponds to a parameterized bound of 0. The y is a sine cubed of theta, and then differentiated x, you've got to remember the chain rule. So you're going to have a times 3 cosine of theta to the second, multiplied by the derivative of cosine, which is negative sine. And let's simplify this. So the 4 and the 3 and the negative can multiply, making negative 12. We've got an a squared, and then we have the integral from pi halves to 0. Okay, it's like sine to the 4th theta, cosine squared theta, d theta. And the last thing you could do to simplify is just flip those bounds and change the sign of the integral, 12a squared, 0 to pi halves, sine 4th theta, cosine squared theta. And the reason I wanted you to simplify and not solve is that this one does get a little bit ugly to solve because you have to use the half-angle identities, where sine squared theta is 1/2 1 minus cosine of 2 theta, and you have to use the fact that cosine squared is 1/2 1 plus cosine of 2 theta to do this antiderivative, and it's going to take a long time. If you feel like you want to do it for fun, go for it, but I think we'll probably focus more on setup, don't solve, just to see that you know the formulas and how they work. Or the ones that you do will be just a lot easier to solve than this. So similar thing here, set up and simplify, but we're not going to solve an integral that finds the length of the curve. X equals t sine t, y equals t cosine t, when t is between 0 and 1. So the thing to remember here is that arc length formula is given by an integral from, well, alpha to beta, root dx dt squared plus dy dt squared dt. So the integral from 0 to 1 square root, this is going to get awfully long, so okay, so dx dt, that will be sine t plus t cosine t, the quantity squared, plus cosine t plus t times negative sine t, that quantity squared dt. And then, holy moly, go square. 0 to 1. Okay, squaring the first thing. We'll have sine squared t plus 2t sine t cosine t plus t squared cosine squared t. That's the first set. Second set, we'll have plus cosine squared t minus 2t sine t cosine t plus t squared sine squared t dt. And now some stuff will get better. So for example, like this 2t sine t cosine t cancels with that one. So that's gone, no big deal. This sine squared t plus that cosine squared t, well, that will equal 1. So let's at least write that much down. We still have the integral from 0 to 1, root, so the purple things, let's write them in purple so we know where they came from. And all the rest of it, we have plus t squared cosine squared t plus t squared sine squared t dt. And you think that must simplify too. And how it works is this, is you can factor out the t squared just from that little group. And then you see that, well, that cosine squared t plus sine squared t is also 1. So this integral simplifies quite a bit to the integral from 0 to 1 root 1 plus t squared dt. And so that's as far as I want you to take it, because the problem from here is now you have to use a trig sub. So you're going to have to let t equal tangent of theta. And remember that then dt will be secant squared theta d theta. And if you change your bounds, we have, well, 0 equals tan theta. That means that theta's got to equal 0. And 1 equal tan theta, that means theta is pi quarters. And I think this doesn't even work out all that well from there, because I believe, so this really is good enough, because what it requires after that is this substitution, and I can tell you right now what's going to happen is I think it's going to become the integral of secant cubed, which then I'm pretty sure involves like integration by parts around the world. It's just horrible, awful, no good, very good, bad, bad, bad. So set it up. The fact that you can simplify it down that much is really, really an achievement. So I think we're good. So set up and simplify, but don't solve an integral that finds the area of the surface obtained if we rotate this asteroid region from the previous example about the x-axis. So we're looking at this part of that asteroid. So we have the surface area formula is the integral 2 pi y ds for rotation about the x-axis. Remember, think that you have the circumference of a slice. The ds tells you the length of that slice. So that's the integral from 0 to pi halves, 2 pi times a sine cubed theta, and then ds gets a little bit complicated. Remember that ds is the square root of dx d theta squared plus dy d theta squared d theta. So let's take the constants out of the integral. All right, dx d theta. Well, dx d theta is 3a cosine squared theta times negative sine theta, that quantity, squared, plus 3a sine squared theta times cosine theta squared d theta. Now squaring that out, we have the square root of 9a squared cosine to the 4th theta sine squared theta plus 9a squared sine to the 4th theta cosine squared theta d theta. Now the best thing you can do with that square root is try to factor out greatest common factors and hope that they square root. So it looks like we have a GCF of 9a squared cosine squared theta sine squared theta. We're left with, after that's been taken out, a cosine squared theta plus sine squared theta, which conveniently is equal to 1. And then everything else inside there can square root. So we have 2 pi a integral 0 to pi halves sine cubed of theta times 3a cosine theta sine theta d theta. So that's 12 pi a squared integral 0 to pi halves sine to the 4th theta times cosine of theta d theta. And if you had more time, this one wouldn't be a terrible one to solve, because you could just do a u substitution for sine of theta. But there's enough in the setup that you have to simplify that I think that this is probably good enough in terms of having some time constraints.